Hey, welcome back. It is time for our next installment in How to Punish Yourselves with Chemistry. Stoichiometry. So in this particular lesson, we're going to take a look at using our balanced chemical equations with a little bit more challenging ones. I kind of introduced it in the last one. So in this one, we're going to do a little bit more of that grams to moles kind of stuff and trying to figure out who's related to who and how much goes in and how much comes out. So make sure you got your calculator ready. If you have a periodic table ready, that's super helpful. And then what you can do is what I would suggest, if you're starting to feel a little confident, hit pause, right? As I introduce a problem, and then you can try to kind of work it out on paper, and I can sort of help you out with the answer. We can check it and see how we did, right? So here we go. Stoichiometry. In terms of what this is, again, a reminder to review, kind of refresh ourselves, that a balanced chemical equation has to be balanced, but a balanced chemical equation is a recipe for a chemical reaction. It tells you what your reactants are, what's going in. It tells you your products and what's coming out. It also gives you that ratio, and that's the key part. It not just tells you what's in and what's out, but how much. And that's really the most important part for us, is to know what are our important quantities that we can get. We want to be able to predict how much product are we going to make, or how much reactant are we going to use up, or how much of a reactant do we need to make a reaction happen. So this is what we're going to do in this particular chapter, or this particular video here, is to take a look at sort of the sequence of events that happens in one of these typical stoichiometry problems. Now, again, stoichiometry, these ratios that we see are always in moles to moles. That's what I've kind of got right over here, right? It's always moles to moles on the screen whenever you're taking a look at those coefficients from the balanced chemical equation. So like this particular balanced chemical equation would be one of these things, CH2S plus 6 fluorine gases produces 1 carbon tetrafluoride, 2 hydrofluoric acid, and 1 sulfur hexafluoride. So if we were going to do this, these would be 1s here and 1. And our units here could be one of two things. It could be molecules, right? 1 molecule of each, but that's really not very useful for us. More commonly, it's going to be moles. It is not in grams. Moles is the unit that's always in terms of what these ratios are. So if we have a question like this, it says how many grams of sulfur hexafluoride could be produced from 1.25 moles of fluorine gas. When we have a question like this, we've always got 2 chemicals that are being specified. If it's got more than 2 chemicals that are being specified, it may be a multi-part problem, but it could be 2 chemicals, and it can be any 2 chemicals. It could be 1 from the left and 1 from the right. It could be 2 from the left, or it could be 2 from the right. So this allows us to sort of translate between any 2 elements, either a reactant and a product, 2 reactants to figure out how much of them that we need, or 2 products if we want to. But typically, oftentimes it's given to you as a product and a reactant, but it can be any 2. And then when requested, remember that sometimes we're going to want to convert to grams using molar mass. That's what MM stands for, molar mass, but not always. So make sure to read the problem and know what units you're looking for. So if I take a look at this one, again, I'm going to use that strategy of always labeling my equation. I'll move this up just a touch so I can get to my tools at the bottom of my screen. My apologies. So I always want to try to make sure that I am, again, looking kind of closely at the way my problem is worded to make sure that I am, like I said, looking at it, at reading the right parts or doing the right parts of it. So I'm looking for grams of sulfur hexafluoride. So I got to kind of look at this thing and go, which one would be sulfur hexafluoride? Well, that one right there is our sulfur hexafluoride. So I want to know this one, and I want to know grams. Notice how it says how many grams of that, not just moles. Labeling my equation, that's a strategy. And how many could be produced from 1.25 moles of fluorine gas. So that's this one, fluorine gas right here, 1.25 moles of this. So that's the conversion I'm trying to do. I've got 1.25 moles of a reactant, I'm trying to figure out how much product can be made. And in this case now, I'm looking for grams of product, not just moles of product. So I'm going to set up my little wonder fraction, right? Start with what you're given, 1.25 moles of F2. And again, it's moles of fluorine gas. Notice how I did not put that coefficient in there. That comes in the conversion section, doesn't come in when you're setting up your problem. You're always just starting with what is the amount that you've got and what's the chemical that you've got. I'm going to make my little wonder fraction line here. There it is. So now again, cross down and convert up. So I have to cross down from moles of F2 and then convert up. Well, if I'm in moles, I can do one of two different things. I could convert to grams of the same compound, grams of F2, not what we're looking for here, or I can convert to moles of a different compound using our balanced equation. So moles of a different compound, SF6. So if we're doing that, because that's what we're starting with here and ending with here, moles of one chemical to moles of another chemical. Again, cross down, that's your original, convert up, that's your new. So what am I trying to go towards? And then for this, what's my conversion for these? It's my recipe. Look at the recipe. This says 6 fluorines are going to produce 1 SF6. Okay, 6 fluorines are going to produce 1 SF6. And that unit is always moles. Whenever you're going from one thing to another in a chemical equation, the unit for that is moles. 6 moles of fluorine gas will produce 1 mole of SF6. Am I done yet? Well, look at where I'm at and then compare it to what I'm trying to find, right? My question mark is for grams of SF6. So I'm in the right chemical, but I'm not in the right unit yet. That means I need to do one more step. So cross down and convert up. Cross down has got to be the exact same unit, moles of SF6, and then convert up. I can convert to now grams of SF6. How can I do that? That's a molar mass step. That's what this is. By the way, this is our mole to mole step. That's when this one was, right? Moles to moles. This is our molar mass step, just to make it easier to talk about who's who. So when I do molar mass, the units of molar mass is always grams per 1 mole. So this is always going to be 1 mole here, and I just need to figure out my grams. So sulfur weighs 32.06, and I have 6 fluorines. 6 times 19.00, yeah, 19.00, 19 equals 146.06, 146.06. Again, remember, for molar masses, we always use 2 decimal places, just so you know. As a reminder, it's been a little while since we've done that. So now we just do our math. 1.25 times 1 times 146.06 divided by each thing on the bottom, so divided by 6. So 146.06 times 1.25 divided by 6. And we get a crazy long number, 30.429166, whatever, 7, continuing. It's our unrounded answer. So now we have to round to sig figs. So look at your original problem for sig figs. Our original problem has 3 sig figs, 1.25. Molar mass does not affect your sig figs generally, and a mole-to-mole ratio is considered exact, so it will never affect your sig figs either. You're always looking at your original problem. We got 3 sig figs, so that would give me 30.4, and then units and labels, FF6. There you go. So 30.4 grams of SF6 could be expected from this particular reaction. So that's a Stoich problem. That's how you do it. Allows you to predict the quantity of a product based upon a quantity of a reactant. So the rest of this, we're going to take a look at a couple other issues, make it a little bit more challenging maybe, but that's really pretty much it. So this is a good spot that if you're feeling confident, this would be where you would hit pause, try it on your own, scratch it on a piece of paper, see how far you get, and then come back and check with me. So I've given you this equation balanced already because it's got some big coefficients. Didn't want to use our time in this particular video to balance the equation. So here it is balanced for you already, and you can tell it's balanced because there's coefficients in there. So what are we trying to find? Okay, start by decoding your problem. How many grams of carbon dioxide? Okay, so I'm finding my carbon dioxide. Here it is. And I want to find grams of this. Okay, this G here, remember, means gas. It doesn't mean grams. L means liquid, gas, etc. So how many grams of carbon dioxide would be produced from the complete combustion of 125 grams of benzene? Now, every once in a while, students will go, what the hell? I don't know what benzene is. How am I supposed to know what benzene is? Okay, so quit panicking and look at the reaction. There's only one thing in this reaction that could possibly be benzene. So take a breath. Well, that's not benzene, that's water. Well, that's not benzene, that's carbon dioxide. That's not benzene, that's oxygen gas. Guess what that is? Benzene. So 1.25, not 1.25, grams of benzene. So now we know what we're going to do. We're trying to convert from grams of a reactant to grams of a product. So now remember, the thing that's important here is that when we see this 2 and this 15 and this 12, those are mole to mole ratios, not gram to mole ratios. So we have to be a little bit careful here. 125 grams of benzene, C6H6. Okay, so when I do this, there's my long-winded fraction line. There we go. Remember, you have to be exact. Grams has to be down here. I know I need to use a mole to mole ratio, but I'm not in moles yet. So I have to get to moles. Moles of C6H6, C6H6. Well, how do I do that? It's a molar mass step. 12.01 times 6, that's the molar mass of carbon, plus 6.06, which is the molar mass of those hydrogens all added up. So that is 78.12. Grams of C6H6 equals 1 mole of C6H6. So we had to do a molar mass step first in this case. Now, okay, where are we at? Moles of C6H6 over here. Moles of C6H6. I can do two things when I'm in moles. I can convert to grams of the same chemical, or I can convert to moles of a different chemical. And this is that case where we can now do our Stoich step, where we can do moles of a different chemical. I can go to my other side of my equation. Why CO2? Because that's what we're looking for in this problem that was specified. Could have been anything else. In this case, it's CO2. So now when we're doing our mole to mole ratio, our M2M step, this is where we use our coefficients from our balanced equation. It's our recipe step. So 2 moles of C6H6, 2 moles of C6H6 is going to produce 12 moles of CO2. 12 moles of CO2. There's our recipe right there. That makes it stoichiometry. This step, mole to mole step, is stoichiometry. Okay. Our last thing that we need to do now, because we're in moles of CO2, is we need to convert to grams, because our problem asks us for grams here. So we're not quite there yet. So I'm going to do moles of CO2 to grams of CO2. Again, when you're in moles of something, you can either convert to grams of the same chemical or moles of a different chemical. Those are your only two choices when you've got that, when we're doing Stoich. So 12.01 molar mass plus 16 for our CO2 is 44.01 grams per mole. Per 1 mole is the mass of carbon dioxide. So there you go. Now we're in grams of CO2. That's the unit we're looking for. We're in the right chemical and the right units. And then now we can just do our final calculations. Okay, again, remember, multiply across the top. And now divide by each number on the bottom. Don't forget to do divided by 78.2 and divided by 2. This is the important one. A lot of times students will do divided by 78.12 times 2. You either have to use parentheses or something. I suggest just if it's on the bottom, hit the divided by key on your calculator, right? That's what this thing is for. Let it do its job for you. So 125 times 12 times 44.01, multiply across the top. Now divided by the bottom, divided by 78.12 and divided by 2. And we get a number. Again, here's our unrounded answer, 422.52304 and more, whatever else comes out in there. And then we look at our original problem for sig figs. We got 3 sig figs in our problem. So let's round our answer. This would be 423 grams CO2. There you go. So that is a grams to grams Stoich step. You can never go directly grams to grams. You always have to do grams to moles. Then you do moles to moles. That's how you have to have a moles to mole step. And then finally you could go moles back to grams. You cannot do this directly. Grams to moles to moles, moles to grams. Pretty consistent pattern for these particular problems. I think. Am I done? No. Okay.